Hello everyone. Today we are going to learn Schrodinger equation in its time dependent form. As we are familiar with the time dependent form from the previous lecture, I'll go for this is the time dependent Schrodinger equation we have derived so far. Now, our aim is to find time independent Schrodinger equation. In order to arrive at time independent Schrodinger equation from a time dependent form, what we are going to do is use the mathematical technique of separating the variables from the wave function. So this is how we separate variables. We have two different variables r and t in the wave function psi, and using the variable separable method we can separate the variables of a function like this. So now we have a spatial part of the wave function and the time part of the wave function. Now once we have this separated form, we apply it in the time dependent Schrodinger equation, which is given in equation 1. So I am going to substitute it, applying to equation 2 in equation 1. So when you substitute, you have to remember that on the left hand side we have only a time differential, and on the right hand side we have only space differential. So when you substitute on the left hand side, where you are supposed to take only time differential, the spatial part will be a constant. So psi of r can be taken outside. Psi of r into dou by dou t of, or dou by dou t can be written as a full differential because we have only a single variable focused. So dou by dou t can be written as a d by dt of phi of t. Okay, so that is the left hand side. So you need not worry about this function because I'm going to divide psi of r into phi of t on both sides after this differentiation. Okay, first we have taken the differentiation. Since we have time differential on the left hand side, space part is a constant. So space part is taken outside and we have IH cut, then d by dt of phi of t. Because we have a single differential of significance, we make it a complete differential instead of the partial differentiation, and divide it with the psi of r into phi of t. So when we divide wave function psi of r into phi of t, we divide it on both the sides. Okay. Now come to the right hand side. Here, as I mentioned, we have only space part, so phi of t is a constant here. Again we have a divided psi of r into phi of t here. Then minus h cut square by 2m del square plus v of r into psi of r, because we have to take a differential of psi of r only here, because del square is only a function of space variable. Now okay, I didn't tell you to cancel these two because on the left hand side we had psi of r as a constant. So psi of r from numerator and denominator will get cancelled. Also phi of t on the right hand side. Now what we have is IH cut d phi by dt by phi of t, and on the right hand side we have 1 by psi of r into minus h cut square by 2m del square plus v of r into psi of r. Now if you analyze this equation, what we have is a single variable on each sides. Here we are worried about only time variable, and on the right hand side we have only space variables. So once we have such an equation, mathematically we can equate both sides separately to a constant. That is based on the mathematics. Okay, so let us equate. Here is the left hand side. IH cut 1 by phi of t into d phi by dt, that is equal to, we take a constant capital E and equate left hand side as well as right hand side. Now we are going to analyze both the sides. So we are just rearranging it. Taking IH cut on the right hand side, we have E by IH cut, and multiply and divide with I, so that we can have I, that is a complex part, in the numerator. So you have I square in the denominator, that means it will become minus. So minus I E by H cut. Now take phi of t, this is dt can be taken to the right hand side. You have a d phi by dt, so dt can be taken to the right hand side, so we can integrate it. This is the integral over the variable phi, and on the right hand side we have integral over t. So integrating d phi by phi, that means it turns out to be a logarithmic function, and on the right hand side it is minus I E by H cut is just a constant. So integral dt is dt t plus a constant c. So you have minus I E by H cut into t. Integral dt is t plus a constant. So whenever you do an integration, you will end up with an additional constant. Now taking exponential, because we have logarithm of phi of t on the left hand side, so taking exponential, logarithm of phi of t cancels, and what remains is only phi of t. Exponential of logarithm is the function itself. But on the right hand side you will have exponential, e raised to minus I E t by h cut into e raised to c, that just turns out to be a constant. Exponential of a constant also will be a constant. So this is the value of phi of t we have arrived. Now coming to the right hand side, that is the space part, we are just rearranging it. Take phi of psi of r to the right hand side. So this turns out to be the time independent Schrodinger equation. So here we don't have any term containing the time variable, and this is the time independent Schrodinger equation. So this looks like an eigenvalue equation, because this represents the Hamiltonian operator, and when a Hamiltonian operator operates on the eigenfunction of it, it results the eigenvalue, the energy, that is the energy eigenvalue, and the wave function. So this eigenvalue equation is our time independent Schrodinger equation. So simply we can write operator H acting on psi gives eigenvalue, that is E, a constant, into psi of r. And from phi of t, from the left hand side we have the value of phi of t, so the total wave function psi of r comma t is psi of r into e raised to minus I e t by h cut. So now we have the eigenvalue and eigenfunction. Now let us check more about the constant. Okay, now we are just going to analyze how this E behaves and the wave function as well. So we have our wave function, complete wave function. Now multiply it with I h cut on both the sides and find the time differential. So I h cut into dou by dou t of psi of r comma t, that is equal to, when you differentiate it with respect to time, we have only this exponential contains time part, so you have to differentiate it. So the constant coming out is minus I e by h cut into exponential of the function itself. So you have an h cut that getting cancelled from numerator and denominator, and there is two i's here, that means I square is minus 1. Already you have a minus here, so it becomes a positive term, and e is something remains. So e into psi of r into e raised to minus I e t by h cut is psi of r comma t. So you can write it as psi of r comma t itself. So e into psi of r comma t. Now what we are going to do is multiply this equation with psi star and integrate it all over the space. So this equation becomes integral minus infinity to plus infinity psi star I h cut dou by dou t into psi of r comma t d2. So if you observe it closely, this actually represents the expectation value of energy operator. This is the definition. So I h cut dou by dou t represents energy operator. So this can be written as a expectation of energy. And on the right hand side you have, we had this one. So integral, integrating, multiplying with psi star and integrating, you have this e is actually a constant. So e comes out and integral minus infinity to plus infinity psi star psi d2 means it is a normalized wave function, so that turns out to be 1. That is the normalization condition. Integral minus infinity to plus infinity psi star psi d2 is equal to 1. That is actually definition, that is a normalization condition you have learned in the formalism, mathematical formalism. So e into 1. That means the constant we had taken is actually the expectation value of the energy operator. So when we measure what actually we find is the expectation value of the energy operator. That is what we understand from the constant we have chosen. Now let us analyze the other properties of wave functions, like calculation of probability. So here we are going to I'm going to tell you that you have n eigenstates and correspondingly n eigenvalues of the Hamiltonian. So when you calculate the probability using the definition of a probability, you know that it is psi star psi. That means here you have n states, nth state we are considering. So psi n star r comma t into psi n r comma t. So apply the value of psi n star, that means psi n star of r into exponential complex conjugate of the exponential, because we have to take psi star here. So it becomes e raised to I e n t by h cut, and psi n r comma t is the normal wave function. So when you can see these two exponentials get cancelled. So what remains is only the spatial part, psi n star into psi n. That means it is mod psi n of r square. So this is actually the spatial part, and the time part has disappeared from the probability while we calculate probability. That means the probability is always a constant. So such an eigenstate where the probability is always constant is named as a stationary state. So in the case of time independent Schrodinger equation, if one is using the eigenfunctions of the Hamiltonian operator or the eigenfunctions of the corresponding operator, then we will have stationary states. That means time independent states. How do we identify a stationary state? Yeah, that the answer lies here. When we have calculated the probability, we found that probability is a constant. So such states are called stationary states. Now, in the time independent Schrodinger equation we have derived, we have a potential part. So for each system we will have distinct potential values. Like for harmonic oscillator you have half k x square, and for each system you will have a different kind of potential energies. So if you want to analyze a system and find its eigenvalues and eigenfunctions, then what you have to do is, all you have to do is substitute the potential in the time independent Schrodinger equation and evaluate the eigenvalues and the corresponding eigenfunctions. And that is the essence of time independent Schrodinger equation. Yeah, now just analyze. Yeah, here you have calculated the significance of E, and we found that the expectation value of the energy is what we are measuring, and the same thing we have opted as a constant in our equation while deriving it. Sorry. Okay, now let us check what is the condition of an expectation value if we have a stationary state. So the derivation of the definition of expectation value of an operator in general is this one: psi of r comma t operator, then psi of r comma t. So the ket vector and the bra vector, and in between the operator of which the expectation value is to be determined is placed. Now this is the expansion of this bracket term. So you will have integral minus infinity to plus infinity, and the wave function, complex conjugate of the wave function. Here you have the wave function. Again you will have the exponential part getting cancelled. Then you have psi n star a psi n ditto. Since this term again contains only the spatial part, you can say that the expectation value of a constant, of an operator is also a constant. Previously we found that the probability is a constant in the case of stationaries. So we have concluded that in the time independent Schrodinger equation we will end up with the stationary state. So here the expectation value is also a constant. We found that if once we have the stationary states, then the expectation value of an operator, of an observable, is also a constant. So using the continuity equation, we can use our conditions. Probability is a constant. Just now we have derived that a probability is a constant. That means rho by dou t of a constant means this term becomes 0. So what we have is a del dot j probability current density is also 0. That means what we have is a bound state. A bound state implies, from all these conclusions, that is probability is a constant, expectation value is a constant, and using the results, all these two results applied here, we have probability current density, that is del of probability current density is also 0. So all these imply that what we are dealing with is a bound state. That means for a state to be bound means it should be confined to a spatial region. So when the space value increases to infinity, this turns out to be 0. That is a condition of a bound state. So when we have a stationary state, most probably we will have a bound state. So in simple terms we can write the condition for a bound state, that is limit r tends to infinity, psi of r will be 0. Okay, now if we have a linear combination of the of various eigenstates in a time independent Schrodinger equation, then the condition is not just like what we have derived just now, that is probability is not found to be a constant because we have different terms while considering psi star psi. For example, you will have a summation over n mod cn square psi of r the whole square, and also you will have cross terms like this, and that will always be containing a time part. So we cannot say that in the case where we have wave functions represented as linear combinations, the probability is not found to be a constant. So we cannot have stationary states in that condition. So this is a special case of the time independent Schrodinger equation we have to be remembered. In normal case, we will have the condition of a stationary state and the probability will be a constant. Also the corresponding state will be a bound state. So this is, we can say that this is a special case. So when we have a random arbitrary wave function which we are always supposed to write it as the existing wave functions, the combination of linear combination of the existing wave functions, then we are not sure about whether the state will be a bound state or a stationary state. So in that case, we end up with cross terms that indicates there is a time dependence exists. So we cannot have the probability getting a constant or the stationary state. So that is all about the time independent Schrodinger equation. So when it is asked for the examination, you have to begin with time dependent Schrodinger equation, use variable separable form, then apply it and formulate the values left hand side and right hand side equating to a constant. Then analyzing left hand side, you will have the value of phi of t, and analyzing right hand side, you will have the time independent Schrodinger equation. So you have to analyze the constant and evaluate the expectation value and also the probability and the expectation value of the observable or an operator in general. So the results arrived are the expectation value is what we measure. Then the probability turns out to be a constant, that means it is a stationary state. Also the expectation value will be constant. So from applying these conditions in the continuity equation, you will have, you will arrive at a bound state corresponding to a stationary state. In a bound state, the wave function will be confined to a particular spatial region. That means if the space term is increased, if that tends to infinity, our wave function vanishes. Wave function vanishes at infinity. So that's all about the derivation of time independent Schrodinger equation.